Hello everyone, I am Dr. N.G.P, Department of Mathematics. In this video, we are going to see set and group theory concept. This video includes definition of set, types of set, group theory, examples of group, and some preliminary learning. First of all, we are going to see what is set theory. A set is a collection of well-defined objects. The objects in the set are called elements, and it is denoted by the letters, capital letters A, B, C. And the elements are denoted by the small letters. The null set is having no elements. It is a subset of every set. You can also call it as the empty set as null set. Next, we are going to see types of set. Let we can take A and B be two sets. Then the union of two sets can be written as A union B. That is a set of all X. That X may be either in A or B. This is a representation of A union B. Next, intersection of the two sets A and B. That is denoted by the symbol A intersection B. That is a set X such that X belongs to A and also X belongs to B. Next, we can see the difference of two sets. For the two sets A and B, the difference of the set is A minus B, that is A difference B, that is X belongs to A and X does not belong to B. Now we are going to see product set or Cartesian product of A and B. If A and B are two non-empty sets, the product set or Cartesian product of A and B is a set of all ordered pairs A, B such that A belongs to capital A and B belongs to capital B. Next, we are going to see equivalence relation. What is the equivalence relation? A subset of A cross A is said to define an equivalence relation on A if it should satisfy three properties. First one is reflexive property. That is, reflexive property means A is related to A. And the second one is symmetric property. That is, symmetric property means whenever A related to B, then B related to A. Then the third one is transitive property. Whenever A related to B and B related to C, then you have to show that A related to C. So the relation R, which should satisfy the three properties, that is reflexive, symmetric and transitive, is called an equivalence relation on the set A. Let us see the definition of group. A group is a non-empty set G together with the binary operation dot called the product, and it should satisfy the following four conditions. The first condition is for all A, B belongs to G implies that A dot B belongs to G. That is called the closure property. And the second one is for all A, B, C belongs to G, then A dot B dot C equal to A dot B dot C. That is, it should satisfy the associative law. Then the third condition is there exists an element E belongs to G such that A dot E equal to E dot A equal to A for all A belongs to G. And the fourth condition is for every A belongs to G, there exists an element A inverse belongs to G such that A dot A inverse equal to A inverse dot A equal to E. That is the existence of inverse in G. Next, abelian group. A group is said to be an abelian group if it satisfies the commutative property. That is, what is commutative property means for every A, B belongs to G, A dot B equal to B dot A. So, any group satisfying the commutative property A dot B equal to B dot A, then that group is called an abelian group. Now we can see the examples of group. Example 1. Let G be the set of integer G equal to etc. the set etc. minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, etc. then G is a group under usual addition. Next, we can see the example 2. Let G be the set of all 2 by 2 matrices AB in the form AB, CD, where A, B, C, D are real numbers such that it should satisfy the condition AD minus BC not equal to 0. Then G is a group under matrix multiplication. So for proving G is a group, we have to check the 4 conditions. First one is closure property, and second one is associative property, and the third one is existence of identity, and the fourth one is existence of inverse. We can check one by one. First, we are going to check the closure property. For closure property, we have to take two matrices in G, that is A, B, C, D, comma, W, X, Y, Z belongs to G. Then this multiplication of these two matrices will give the form AW plus BY, AX plus BZ, DY plus CW, CX plus DZ. That is also belongs to G. Then we can check the second condition. Second condition is associative law. Associative law of multiplication holds in all matrices. Therefore, it holds in G. Then we have to check the identity property. Let Take the 2 by 2 matrix 1 by 0, that is identity matrix 1 0 0 1 belongs to G. Consider A B C D and 1 0 0 1. So multiplication of these two matrices will give A B C D, and also identity matrix, multiplication of identity matrix with the given matrix, that will give the given matrix A, B, C, D. Therefore, the identity matrix 1, 0, 0, 1 is the identity element of the group G. The inverse of the matrix A, B, C, D is D by AD minus BC minus B by AD minus BC minus C by AD minus BC and A by AD minus BC. Now consider the multiplication of the given matrix with the inverse matrix, that will give the identity matrix 1 0 0 1, and also consider the inverse of the given matrix and the given matrix, that will give the identity matrix 1 0 0 1. Therefore, the inverse matrix D by AD minus BC minus B by AD minus BC minus C by AD minus BC, A by AD minus BC is an inverse element in G. Therefore, G is a group under matrix multiplication. Now we can see some preliminary lemma. Lemma 1, let G be a group, then the first condition is the identity element of G is unique, and the second is the inverse element of G is unique, and the third one is for every A belongs to G, A inverse the whole inverse equal to E, and the fourth one is for every A comma B belongs to G, A dot B the whole inverse equal to B inverse dot A inverse. Now we can prove one by one. Now we will prove the first part of the lemma. The first part of the lemma is the identity element of G is unique. Suppose there exists two identity elements E, F and G. Then A dot E equal to A equal to E dot A. Mark this is equation number 1. And F is also an identity element of G. Therefore, A dot F equal to A, that equal to F dot A. Mark this is equation number 2. From the equations 1 and 2, we can get A dot E equal to A dot F. This implies E equal to F. Therefore, the identity element of G is unique. Now we are going to prove the second part of the lemma. For proving the second one, we can take X and Y be two inverse elements in G. Then by the definition of a group, we can write A dot X equal to E, that equal to X dot E. And also we can write A dot Y equal to E, that equal to Y dot A. From the equations 1 and 2, we can write A dot X equal to A dot y. That implies x equal to y. This proves the inverse elements of G is unique. Now we will prove the third subdivision, A inverse the whole inverse equal to A. For proving this one, consider A inverse dot A inverse the whole inverse that equal to A inverse dot A that equal to E. That implies A inverse the whole inverse equal to A. Now we can move on to the fourth subdivision, that is we have to prove A dot B the whole inverse equal to B inverse dot A inverse. So for proving this one, we have to consider A dot B dot B inverse dot A inverse equal to, that we can write it as A dot B inverse dot A inverse. We know that B dot B inverse equal to E, therefore that implies that equal to A dot E dot A inverse. So that equal to A dot A inverse is identity. Therefore, A dot A inverse equal to E. Therefore, B inverse dot A inverse equal to A dot B the whole inverse. Now we move on to lemma 2. Given any two elements A and B in the group G, then the equations A dot x equal to B and y dot A equal to B have unique solutions for x and y in G. In particular, the two cancellation laws A dot U equal to A dot W implies U equal to W, and U dot A equal to W dot A implies U equal to W holds in G. That is, left cancellation and right cancellation laws holds in G. In this video, we learn what is set, types of set, group theory, examples of group, some preliminary lemma. Thank you for watching this video.